This is continuation of our discussion on contours. In the previous module, we defined what are curves in the complex plane, what are simple curves, and what are simple closed curves. In this module, we will continue our discussion, and at the end of this module, we will be able to define precisely what are contours in the complex plane. So let's begin with our discussion of contours. Now, let's recall what is a curve in the complex plane. A curve in a complex plane is given by x of t plus iota y of t, and t varies from a to b. Now, this x of t is definitely a real valued function. A real valued function, and of course, this y of t is also a real valued function, and of one variable t. Here t is basically the parameter. Now, the first thing that we are going to define in this module is the differentiability of a given complex valued function of this form. Okay, basically it's a function of one variable. In fact, it's not variable, it's a parameter t. Now, this function is said to be differentiable on this closed interval a b if both functions, real valued functions x of t and y of t, are differentiable on this closed interval a b. And of course, since there is nothing, okay, so if we say that this is the parameter line, okay, so this is the parameter line, and as we are evaluating the points of this parameter line, then we are getting a path in the complex plane. Okay, so for example, if we take the value a, then we get this f of a in the complex plane, and moving on and evaluating the values, and we stop at f of b. Okay, so and of course there is a direction of motion, and so basically that's how we get this curve in the complex plane. Now, at this point a, there is a problem that we cannot calculate both side limits. So there is no notion of derivative at this point a, but we can calculate one side derivative on a. So we can calculate this side of derivative, and on b we can calculate the derivative from this side. So we talk about one-sided derivatives on points a and b, and apart from these points a and b, we can calculate the derivatives on all other points between a and b. Okay, so that's how we define the differentiability of a given function of the form x of t plus iota y of t. So can we check the differentiability of the following curve? The x of t is given to be mod of t, and y of t is basically t square. Now, t square is basically a polynomial, so it is always differentiable. So it is always differentiable, and we can also check that it is one-sided differentiable on -1 and -1. Okay, now what about mod of t? So if x is equal to mod of t, now if we discuss the properties of this function, okay, so let's discuss this real valued function of the parameter t. The graph of this function in the real plane, real coordinate plane, is given like this shape v. Okay, now we know that this function is not differentiable at 0. Okay, so mod of x, mod of t is not differentiable here. So there is a point in the domain which is 0 where one coordinate of this function, which is x of t, is not differentiable. So we can say that this curve is not differentiable in this interval -1 to 1, because if we are saying that the function is differentiable on a given interval, then it has to be differentiable at each and every point. So this implies that z of t is not differentiable in the interval -1 to 1. And of course, if you redefine the interval to exclude this number 0 from the interval, then you can say that this is a differentiable function. Now let's check the differentiability of the following curve. X of t is cosine t, y of t is sine t, and we know that x of t, which is cosine t in this case, is always differentiable. Okay, so that's why we can say that this is a differentiable function on this interval as well. Differentiable on this interval 0 to 2 pi. And of course, we can easily check that it is one-sided differentiable on 0 and 2 pi as well. Similarly, we also know that the sine of t is always differentiable, and it will be differentiable on the closed interval 0 to 2 pi as well. So both of these functions are differentiable on this interval, and of course one-sided differentiable or at the endpoints. So that's why we say that this function z of t is differentiable on the closed interval 0 to 2 pi. Now let's move on to our next terminology, which is the smooth curve. Okay, so all of these terminologies are needed to define the term contour. Now a curve is said to be smooth if z prime of t is continuous and non-zero on the interval, of course, interval AB. Now the first condition is z prime of t not only exists, but it is a continuous function. So this is the first condition. And the second condition is z prime of t is not equal to 0 for all t belongs to this interval a to b. And if these two conditions are satisfied, then we say that the curve is smooth. Now let's check if this curve is smooth or not. Now let's calculate z prime of t. Now z prime of t is the derivative of t square, which is 2t plus iota 3t square. And of course this exists because these are just polynomials. And we can also see that z prime of t is also basically the coordinates are polynomials. Okay, so these are polynomials, and polynomials are always continuous. So this implies that z prime of t is continuous. So the first condition is satisfied. Okay, so the first condition is satisfied. Let's talk about the second condition. So in the second condition, we require that z prime of t should not be equal to 0 for all t belonging to -1 to 1. Now there is a point in the interval which is 0, and we can easily see that z prime of 0 is going to be equal to 2 of 0 plus iota 3 0 square, which is equal to 0. Okay, so this implies the second condition is not satisfied. So this implies that z of t is not smooth. Now we are able to define the main terminology of this sequence of two modules, which is the contour. A curve C is said to be a contour if it is constructed by joining finitely many smooth curves end to end. So for example, if there are n curves, then we can join them end to end. So in other words, the terminal point of C1 is basically the initial point of C2, and similarly the terminal point of C2 is the initial point of C3. The terminal point of Cn minus 1 is the initial point of Cn. Now for example, if we consider this curve C1, this is smooth because it's just a straight line. And let's say if we have some other curve, this one, okay, let's call it C2, okay, and let's say we have another curve, let's say C3, and let's say we have another curve, see this, and let's say this is C4, and if we join them, then we will get a contour. Okay, so let's see how to join these things. So it should be end to end. So this is C1 now. Okay, and for C2, just join the terminal point of C1 with the initial point of C2, so we get this thing. And moving on to C3, so we can just join C3 like this. And moving on to C4, so what do we get? So we get something like this. So this is C4. So this is basically a contour made of 4 curves. So we can represent this contour in the following way. So we can say that this is C, which is equal to C1 plus C2 plus C3 plus C4. So this is C2. Okay, so that's how we construct a contour which is composed of smooth curves. So all of these C1, C2, C3, C4 should be smooth curves. Okay, so their derivative should be continuous and their derivative should be non-zero. Now let's try to construct a contour. So basically we want to find a polygonal path from -1 plus iota. So from this point to 3 minus iota to this point. Okay, so polygonal path means we want to find out a path which is made of straight lines. Okay, so to construct this path, we first find this line segment from -1 plus iota to -1. Okay, so let's call it C1, and then we construct another path from -1 to 1 plus iota. Okay, so let's call it C2, and then we construct another path from this 1 plus iota to 3 minus iota. So let's call it C3. Okay, now C1 plus C2 plus C3 basically gives us a polygonal path C from -1 plus iota to 3 minus iota. And of course we chose this point 1 plus iota. We can choose it to any other point. So for example, we can also take it to be this point, which is 3 plus iota, and then we will move on from this point in this direction. Okay, so we can also use this path as well. Okay, so there are many options of doing this thing, but we are just choosing these curves C1, C2 and C3 in this way. Okay, so our next task is to find the equations of the C1, C2 and C3. So to find the equation, there is a very useful simple calculation that the parametric equation of a line segment from Z0 to Z1. Okay, so Z0 to Z1 line segment has the following parametric equation. Okay, so it's very simple to derive it, and we can also check its credibility by putting t is equal to 0. So when we put t is equal to 0 in this case, let's call it Z of t. So what is Z of 0? So from here we can easily see that this is Z0. So this is the initial point. And if we move on and if we take t is equal to 1, then we can easily check that Z of 1 is going to be equal to Z0 plus 1, Z1 minus Z0. So Z0 and Z0 will cancel out and we get Z1. So Z of 1 is basically Z1. So it is basically a line segment and the direction of motion is basically Z0 to Z1. So this is the parametric equation. So we can use this calculation to find the equation of the line segment C1 from -1 plus iota to -1. So in this case, Z0 is going to be -1 plus iota and Z1 is going to be equal to -1. Now let's call the parametric equation to be Z1 of t, and we want to find out what is going to be x of t plus iota y of t. Now let's replace the value of Z0. Z0 is -1 plus iota plus t, and Z1 is -1 minus -1 plus iota. Now let's simplify this thing. So -1 plus iota plus t, and this -1 and this +1 will cancel out each other and we get minus iota. So this is going to be equal to -1 plus iota minus iota t. Now if we want to write it down in the standard form, x of t plus iota y of t, so we separate the real and the imaginary part. So the real part is -1 plus iota 1 minus t is going to be the imaginary part. So x of t in this case is -1 and y of t in this case is 1 minus t. And of course we can see from here that it is a smooth curve. Okay, so the line segments are defined by linear equations, so this is always a smooth curve. So that's what we get. So z1 of t is -1 plus iota 1 minus t. And similarly we can in this case take z0 to be equal to -1 and z1 to be equal to 1 plus iota, and using these values once again in this case we can easily see that z2 is going to be equal to -1 plus 2t plus iota t. And similar in the third case, z0 is going to be 1 plus iota and z1 is going to be equal to 3 minus iota. Replacing these values in this standard formula for the equation of the line segment, we will get the equations of C1, C2 and C3 in the following way. So we have a polygonal path from -1 plus iota to 3 minus iota, and we approach or we follow the journey by using 3 different line segments, and as discussed earlier, we can also choose some other path as well. So that's how we construct this contour. So I'm saying that it is a contour because C1, C2, C3 are basically smooth functions, and it is left as an exercise to check that whether these curves are smooth or not in the given intervals. Now, there is a simple notation in the definition of the curve as well. So if you are given a curve, then what about the opposite curve? So the notation is we denote the opposite curve with minus c, and its parametric equations or its defining function can also be found by just replacing t with minus t. So why it is the case? So it's a very simple idea. Okay, so let's say this is c, and z1 of t is basically z1 of a is basically the initial point, and z1 of b is the final point, and you move in this direction and you move like this. Now if you want to find a parameterization of the same path where we follow the same geometrical path but the direction of motion is opposite, then we just replace t with minus t and change the interval from a to b to minus b to minus a. So this is the trick that will be helpful for us when we will be trying to evaluate different contour integrals. Now what's really happening in this case? So let's see what is z2 of minus b, because this is the initial point. Okay, so let's see what is z2 of minus b. So it is going to be equal to x of minus b plus iota y of minus b. So this is going to be equal to x of b plus iota y of b, and it is the same as z1 of b. So basically this is the initial point, but it is the final point of z1 of t. So this is the initial point for z2 of t. Okay, so z2 of minus b is basically the initial point. And similarly we can check that the final point is minus a, and it is going to be equal to z1 of a. So this is z2 of minus a, which is the final point. And the rest of the geometrical points are going to be the same, but we are now moving from z1 of b to z1 of a. So the direction of motion is opposite, and we denote this opposite curve with minus c. Okay, so geometrically minus c traces out the same set of points in the plane as c, but in the reverse order. Now there is a simple calculation that we have seen in calculus of multivariable functions as well. So if you are given a curve defined in the following way, x of t plus iota y of t, then the parameter t varies from a to b, then the question is, can we find the length, the arc length of this curve? Of course it's very simple to find lengths of straight line segments, but if it is a curved path, then it is a kind of complicated, and for that we have the following formula to calculate the arc length. So x prime of t square plus y prime of t square square root a to b. Now this integrand is basically a real valued function because there is no iota involved in here, and x of t is a real valued function. Just take the derivative, square it, add them together, and we can easily calculate this thing. Now x of t is x prime of t is continuous, y prime of t is continuous, and the square of them is continuous, the sum of them is continuous, and at the end the square root of them is continuous. So that's why this integrand is a continuous function, and we know from real analysis that continuous functions can be integrated very easily. If we take in particular z of t to be equal to cosine t plus iota sine of t, and if we want to calculate the arc length, then we can easily use this formula, 0 to 2 pi square root the derivative of cosine t is sine t, so it becomes sine square of t. Derivative of sine t is cosine t, so cosine square of t dt. Now this is going to be equal to 1, so 0 to 2 pi, so this is just dt, and this is going to be equal to t 0 to 2 pi, which is going to be equal to 2 pi. And we know from our formula that the arc length of a circle of radius 1 is 2 pi. So in general it is 2 pi r, but if the radius is 1, then it is 2 pi. This is the end of our discussion on the topic of contours. And in this series of 2 modules, we define what are contours. In our next discussion, we will use this definition of contour, and we will try to define precisely how we integrate a given complex valued function on a contour.